So in my previous segment, we just found out that the derivative of the function y equals x to the fourth power is 4 times x to the third power. d on dx applied to x to the fourth gives me 4x cubed. Well, what's this pattern telling me? My derivative of the function y equals x was just a constant 1. My derivative of the function y equals x squared was 2 times x. My derivative of the function x cubed was 3x squared. It seems like every single time I'm going down by 1 in the exponent, but then I also have to multiply by some coefficient. My pattern is telling me my derivative should be the old exponent times x, and the new power is 1 less than the old power. So my formula says the differential operator, d on dx, applied to x to the power n, should be equal to n times x to the power n minus 1. So this is our power rule. And this is true for all values of n. I'm going to motivate this in another one of my videos on my own slides in just a bit, so do look for that. Let's use this though. We have this rule, let's try it out, break it in. Let's say I have the function f of x equals x to the 6th power, then my derivative is going to be f prime of x is 6x to the 5th power. See, this isn't too bad at all. I did not have to use limits because I know the rule. Okay, let's keep going. If y equals x to the 1000 power, then y prime, here we're using the prime notation for derivatives, y prime is going to be 1000x to the power 999. Nice. How's about y equals a function of a different variable? How about t as our independent variable? We can do that. If y is equal to t to the power 4th, then my dy on dt is equal to 4t to the 3rd power, or 4t cubed. So again, we decrease the power by 1, but we save the old exponent, and we write that now as the coefficient in front of the function, right? I take the 4 down, I might say, because we write our powers in superscripts. I now have 4t cubed. And notice here that the slides are using the different notations for the derivative. If my original is written in terms of f of x, in function notation, I write f prime of x. If I'm writing in terms of dependent and independent variables, I can just write y prime. And here, because we're using a different independent variable than the traditional x, we've used the Leibniz notation dy on dt. Those all still mean derivative, just slightly different ways to write it. And again, different majors have different traditions for this kind of stuff. So in my class, I'll try to switch between them just so we can get a little bit more familiar. When you go on to your other courses, they might actually pick just one of these that they'll use throughout. Here's another one. Again, we're using a different independent variable. So it must be that r is my independent variable. I'm calculating d on dr, that's my operator, and I'm applying it to the function r cubed. Well, that will give me 3 times r squared. I just bring down the power and I've got 3 times r raised to the power 2. Nice. Now, spoilers, this power rule actually works for any power. My exponent here doesn't have to be a whole number, right? It could be negative. It could be 0. It could be rational numbers. It could be irrational numbers. for any possible real number, still calling it n, the derivative of the function x to the power n is going to be n times x to the power n minus 1.